This is the lecture over chapter 8. What we have been doing up to this point is we've been gathering information uh, to see exactly what happens when you put something in the way of a beam of radiation. You know, how is that radiation generated has been a part of it, but now we're looking at what happens when you actually point that beam of radiation at something. And now, initially here, what we've been looking at in chapters 5 through 7 is we've been ionizing air. And when you ionize air, we've been getting a pretty good look at what sort of radiation is produced. But we're not going to be taking a beam of radiation here in radiation therapy and pointing it at air. We're going to be pointing it inside, uh, a phantom or eventually a human being. So what happens when we do that? How can we take the information that we see when we just ionize air and translate that into what happens in something that is more dense than air? And so that's what this chapter is trying to get at. It's trying to get at how do we define this? What is it? What is the process for correlating what we have going on in air with what will happen if we put this inside, say, a phantom? So we need to go over a few points here in order to figure out what it is that we need to do in order to be able to make that transition. So the first thing here that we're going to be looking at is that absorbed dose is going to be the new unit that we're looking at. We're no longer looking at exposure. If you go back and if you look at what it is that we've done before, we have been looking at exposure. So how much charge is going to be released in the air when we do this. Now we're going to be looking at what happens when that charge gets released inside a thicker substance. So we're going to be looking at absorbed dose, and that's going to be defined as the energy absorbed per unit mass. And that's also going to be an SI unit, and that is going to be referred to as the gray. 1 gray, of course, is going to be equal to 100 centigrade, just like 1 meter is going to be equal to 100 centimeters. And if you divide it into 100 parts, that's where it comes from. This is also going to be equal to 100 rad, and it's also going to be equal to 1 joule per kilogram. That's going to be the standard unit that we're looking at. So how do we convert from Rankins, which is going to be exposure, into the other units? Well, we have a way to do that for Rankine to rad, and that conversion factor for air, you can see the F here, F sub air, is going to be equal to 0.876 rads per Rankine for all X-ray and gamma radiation. For any specific medium, we're going to be looking at the Rankine to rad conversion factor as being 0.876 times the ratio of the average mass energy absorption coefficient for that medium to that for air. So now we have a way of being able to correlate that exposure into dose by taking a ratio of what is released in the medium into that is released into the air. So for low energy X-ray beams like orthovoltage, superficial, the absorbed dose in bone is going to be 2 to 4 times the absorbed dose in soft tissue. Now, why is that? It's because of the photoelectric effect. For these particular energies, this is the effect that's going to dominate. And since we're looking at Z cubed, and since bone is going to have a higher atomic number than most other soft tissue that we're looking at, we are going to be looking at quite a bit of absorbed dose. So the effective atomic number here for bone is 12.3, and for soft tissue it is 7.6. May not look like much of a difference, but when you start to cube it, then you get a significantly deeper impact. Now that's for the low energy X-ray beams. Obviously, we're going to be treating with megavoltage photon beams, and the absorbed dose in bone is only slightly higher than for soft tissue, because in this range, we're going to be looking at the Compton effect. That's the one that's going to be dominating. So while this Compton effect is going to be independent of Z, it does depend on the number of electrons per gram. And because of that, bone is going to have a slightly fewer number of electrons per gram than soft tissue. Now, we need to get on to another concept here called KERMA. And this stands for kinetic energy released in mass. And this is going to be the sum of the kinetic energies of electrons and positrons released by photons in a medium per unit mass. So the unit of KERMA is going to be the same as that as dose. It's going to be gray. This is going to pertain only to photon beams. It is also going to be proportional to the photon energy fluence. It is going to be the maximum at the surface and decreases exponentially with depth. Now that would make sense because your photon fluence, basically the number of photons that you've got coming in for a particular space, is going to be the highest whenever it first strikes the surface, because when that happens, you've got all of the photons there. As this thing starts to make its way through a patient or a phantom, those photons are going to be absorbed, scattered, what have you. And that's going to reduce the fluence. So if we're going to say that KERMA is proportional to the fluence, then that's going to be where it's at its greatest. So for megavoltage beams, dose is going to be less than KERMA at the surface. It's going to build up to a maximum value at a certain depth, depending on the energy. With a further increase in depth, it achieves a transient electronic equilibrium and decreases exponentially. In the transient equilibrium region, dose exceeds KERMA but decreases at the same rate. Now, that's a pretty involved paragraph here, and let's see if we can find a graph here that kind of helps to illustrate that. Take me a little bit here. Here we go. Figure 8.1. So you can see here the relationship between absorbed dose, which is going to be D, and the collision KERMA for a megavoltage beam. You can see here that the collision KERMA right here is going to be decreasing all the while, but as you increase your depth, or when it penetrates, you can see here at the surface that it's a certain amount, and as it goes along, eventually it's going to decrease exponentially, but it will always be decreasing. This is the point at which it is the maximum. Now, if we're looking at absorbed dose, the absorbed dose will not have a maximum here. It takes time to build up. And at some point here, it's actually going to surpass the amount of collision KERMA that you have with this particular beam. So once it exceeds that, it's always going to be greater than that, but it's always going to be decreasing at about the same rate here as the collision KERMA. Now, this beta value here that it's talking about, this is going to be the ratio of D, the absorbed dose, and the collision KERMA. And at this particular point where it crosses, beta is going to be equal to 1. So over here, you can see where the dose is less than the collision KERMA, so it's going to be D divided by the collision KERMA. you can see as it increases, then beta is going to become greater than 1, and then decrease, or the separation here is going to be pretty much the same. So this is something, and the CEP here is a complete electronic equilibrium. In other words, you have as many electrons being scattered into a place as you see coming out. So these are the relationships here that you need to be aware of. Now, there's a lot going on in this particular section, and it's trying to set the stage for what you guys will be looking at coming up in the next course that you're going to be taking. So this is going to try to set a few of the parameters here, primarily just trying to get you introduced to the idea of we're going to take exposure and we're going to start relating that to dose within the patient. So calibration and error. Low energy beams up to cobalt 60. So we're looking at orthovoltage, superficial, that kind of thing. These may be calibrated in air in terms of exposure in Rankins. Now the exposure is going to be converted into dose in free space, or dose to a small mass of tissue just sufficient to provide electronic equilibrium. We need that condition in order to be able to do our measurements, but we don't really want to perturb the beam that much further. So by multiplying dose in free space with a certain factor called the backscatter factor, we can figure out what D max, or the dose at the depth of maximum dose in a water phantom is. Now, there's a lot of discussion going on in Chapter 9 about this. This is just primarily to get you introduced to the idea that we can take exposure for these particular types of beams, and we can figure out what the actual dose is going to be in the patient. Now, there's a very important principle that comes about with this particular type of study, and that is called the Bragg-Gray cavity theory. Now, BG for short, don't think of the band, I'm dating myself here, but the principle of the Bragg-Gray cavity theory is going to be that ionization produced in a gas-filled cavity, or an air cavity of an ion chamber, placed in a medium, is related to the energy absorbed in the medium surrounding the cavity. That relationship involves the ionization charge produced per unit mass of a cavity gas, and the ratio of average mass stopping power of electrons traversing the medium to that of the electrons crossing the cavity gas. And any perturbation in electron fluence caused by the presence of the cavity will do a correction for it. So the idea here is that we're trying to figure out, if we take a chamber and we put it inside a particular cavity, say within a medium, and we can figure out what the exposure or what the amount of ionization that's produced, we can then tie that to the amount of dose that is being produced within that medium. That's what this is trying to get across. Now, are there going to be certain conditions that we have to meet? Sure. But if we can do that, then we can accurately determine what dose is going to be delivered under what conditions. And that's what this is going to be about. That's a lot of what you see physicists do in the clinic, particularly when it comes to phantoms, when it comes to measuring with certain devices or whatnot, is going to be tied back to this particular principle. So the problem that we have here is that exposure in Rankins cannot be measured accurately for photon beams that are above 3 MeV. And it says here generally not above cobalt 60. That's going to be a problem, because what is it that we're delivering to the patient? We're going to be delivering, in many cases, 4 MeV or above. In many cases, you've got 6, you've got 10, you've got 18, in some cases 25. So we can't really get information about what sort of dose these beams are depositing based purely on exposure here. So if we can't do it with exposure, what we can do is we can imply or start to work with the Bragg-Gray cavity theory, because there is no limitation of energy or the type of ionizing radiation in the measurement of absorbed dose. We don't have a limitation on any of that. So that allows us to be able to get information on these specific types of beams. Now, if we can get information about the type of dose that's being delivered with those particular beams, what is the methodology? How do we go about measuring these things? And that's where these calibration protocols come into play. The calibration protocols that we see, TG21, TG51, IAEA, TRS 398, I'll say that 5 times fast. All of these are going to use the Bragg-Gray cavity theory. Now, there are some other details here, like the effective point of measurement for a cylindrical chamber of internal radius r, a radius of photon beam is displaced by 0.6 r from the center and towards the source. That's the kind of thing you probably won't end up using too much. For electron beams, is probably half the radius. Yeah, that's a side note there. That's something you can, just kind of keep track of if you want. For a plane parallel chamber, the effective point of measurement is going to be at the front surface of the cavity. If we're looking at TG21, this was written back in 1983. We no longer, while we can use it as a reference, and it's not to say that we need to throw it out completely, it's been superseded by TG51. And TG21 sort of implies here that this task group, that's what the TG stands for, that the task group, the lower number here means that it was done before the one with the higher number. So for TG21, it's going to require chamber calibration in terms of air karma, or N sub X, exposure calibration factor for a cobalt-60 beam. N sub gas, or the dose to cavity per unit charge of ionization, is calculated from that, from N sub X and other factors related to the chamber design. We're not really going into that too much. I'm just going to sort of give you a general overview of what that's about. There are some basic equations, which if I design some problems, we can go over. I'm not exactly sure how much you guys are going to take away from this. I certainly don't want you to be able to calibrate a machine. That's not what you're here for. But you do need to have a general sense of what it is that goes into making sure these machines are calibrated correctly. And this is the process for doing that. Now, TG51. The major difference here is going to be the chamber calibration, which is going to be based on absorbed dose to water rather than air. Because when we're looking at the higher energy beams, it is more preferable, if not demanded, that you start measuring things in water, because, as I said, as you get above 3 MeV, the exposure in air doesn't really allow us to be able to measure these beams accurately. So, as you can see here, it's a little difficult to see with this level of magnification. So you can see this term here is the absorbed dose to water calibration factor for the chamber determined in a cobalt-60 beam under reference conditions. Now, the beam quality for photon beams is going to be specified by percent depth dose for the photon component of the beam at 10 cm depth of water. This is going to be a pretty key measuring point. So if you've ever seen those big, huge tanks that the physicists will use to fill up with water or whatnot, it is because they're going to be measuring at a particular depth in water. And it will be all types of different depths, but their reference here for photon beams is going to be at 10 centimeters deep. Now, the beam quality for the purpose of electron beam calibration is going to be specified a little differently, and it's specified by the depth of the 50% dose in water, or R50. So the calibration of a photon beam is performed at 10 cm depth in water and then converted to dose at a reference depth of maximum dose, or Dmax, by using percent depth dose. And again, we're going to get into this into the next semester. It won't be this one, but you're going to hear the term PDD, which is going to be referring to percent depth dose, or TMR, tissue maximum ratio, at 10 cm depth. So again, the calibration of the photon beam is performed at 10 cm depth in water and is converted to dose at a particular reference depth, Dmax, by using a percent or a PDD or TMR at 10 cm depth. So you're going to use that as a reference. They're going to figure out what Dmax is, and you're going to be able to compute at several different levels or depths as you go through. That's the point of all of those. Now, the sensitivity of the monitor chambers is going to be adjusted to give the Dmax divided by mu. They're going to want that to be close to unity for a 10 by 10 field at an SSD of 100 centimeters, or an SAD of 100 centimeters, depending on which type of calibration you want to go with. That's their goal, is to be able to get this as close to 1 as possible. Now, the calibration of an electron beam is going to be performed at a reference depth given by this particular formula. It is then converted to dose at Dmax by using PDD at the depth or reference depth. And the calibration is going to be set to give, again, that same ratio close to unity for a 10 by 10 field size at SSD is equal to 100. Now, the basic equation for calibration of photon and electron beams is going to be given in equation 8.47. Now, it's pretty complicated. There's a lot of factors going on with that. And we can visit that. We can take a look at that just to make sure you guys see the different components. But I'm certainly not going to ask you to use that in order to be able to transfer to a specific situation. It's going to be there for your reference, for you to be able to understand where a lot of this data is coming from. Now, if you want to look at the difference in measured dose between TG21 and TG51, it's going to be less than 2% for photons, could be as much as 5% for the electron beams. Electrons are a little bit of a different animal. For the IAEA TRS 398, I'm not precisely sure exactly how much that is going to be used as opposed to TG51 here in the States. There are certain differences, like the beam quality specification is going to be TPR rather than percent depth dose. The basic equation for calibration of photon and electron beams is going to be the same as TG51, except for the notation. Got to be a little bit different somehow, right? Now, exposure rate constant. Exposure rate constant is defined as the exposure rate from a radioactive source of point size and unit activity at a unit distance. So the unit is going to be Rankine squared meters divided by the hours divided by Curie. What that's going to mean is Rankines per hour at a distance of 1 meter from a point source of activity of 1 Curie. Now, the exposure rate constant is unique to every radioactive source. It depends on the photon energies emitted in the decay scheme, their energy absorption coefficients in air, and the number of photons per decay of respective energies. Now, we've talked about what sort of standard we're looking for here in order to be able to measure beams. We've talked about the idea of changing exposure or ionization into absorbed dose. And so we've shown what it is that we want to be able to measure. Now we are going to talk about how that is going to be measured. So there are several different ways in which to do this. And in order to be able to measure that kind of thing, you need a dosimeter. So what different types of dosimeters do we have out there? Well, we have absolute dosimeters, and this absolute dosimetry means that the dose is going to be determined from the first principles without reference to another dosimeter. It's not relative to what anybody else says. It is going to be relative to the conditions under which we measure something, and knowing enough about that particular method of measurement to be able to say, okay, this can compute what it is absolutely, and we don't have to depend on any other device in order to be able to say that this is what the exposure or what the measurement, dose measurement is going to be, period. We have free air ionization chambers, specifically designed spherical chambers of known volume, like at the National Institutes of Standards. We have the calorimeter and ferrous sulfate, or the Frick dosimeter, and these are all examples of absolute. They are also called primary standards. In other words, this is going to be the standard by which you measure something else. And that brings us to the next one, secondary dosimeters. These require calibration against a primary standard. So if you've got something that is an absolute standard and you've got a secondary dosimeter, you want that calibrated against that absolute dosimeter or that primary standard. Examples are going to be thimble chambers, plane parallel ion chambers, TLDs, thermoluminescent dosimeters, diodes, and film are also considered to be secondary dosimeters, but they are used primarily for relative dosimetry. They require calibration against a calibrated ion chamber, as well as appropriate corrections for energy dependence. And there are other conditions that may affect their dose response characteristics. So you want to be able to make sure these guys are in line with these guys. TLDs, no doubt you've heard the name mentioned. So the most commonly used TLD consists of lithium fluoride with trace amounts of impurities, magnesium. It is available in many forms and sizes for use in special dosimetry situations like powder capsules, extruded rods or chips, and crystals embedded in Teflon or silicon discs. It is reusable if properly annealed and recalibrated in terms of its dose response curve. Again, probably a little more techy here than what you would want to see, but if we know what the dose is relative to a certain response in with the TLD, if we have a chart of that, then we can figure out, given whatever information we find from the TLD, we can figure out what the dose is. Now, the response is almost independent of energy in the megavoltage range of photon and electron beams used clinically. However, the dosimeter form and size may affect dosimetry for certain beams and irradiation conditions due to effluence perturbation. Another device that we need to look at are diodes. And these are silicon PN junction diodes. They're well suited for relative dosimetry of electron beams, output constancy checks, and in vivo patient dose monitoring. So their higher sensitivity, instantaneous response, small size, and ruggedness offer special advantages over ionization chambers in certain situations. So in other words, it might be more to your advantage to use diode than some other device, like an ionization chamber. Their limitations include energy dependence in the photon beams, directional dependence, thermal effects, radiation-induced damage with prolonged use, and the modern diodes try to prevent or minimize some of these effects. But unlike ion chambers, diodes do not require high voltage bias in order to collect the ions. In other words, you don't have to set the stage in order for these guys to be able to do their job. Now, a lot of physicists that I work with will say that film is just your gold standard. This is the one by which everything else should be measured. Radiographic film is one of these, and then you also have down here radiochromic film. If we're looking at radiographic film, the sensitivity depends on the size of the emulsion grains, the little crystals of silver bromide within them, and the quality and the type of radiation. So slow speed films, small grain size, such as these, are suitable for relative dosimetry, provided their sensitiometric curve, also known as the HD curve, is predetermined in comparison with a calibrated ion chamber. In other words, if you know how this curve accurately represents what's going on in the film, and that's been measured against some sort of primary standard, then you've got yourself something that you can use. Processing conditions must be standardized, and any air pockets between film and a jacket must be eliminated to avoid artifacts. Film is one of those things that you don't, it can be very sensitive, and you want to treat it as nicely as you can. Optical density is given by the log base 10 of your initial intensity divided by the transmitted intensity. It's measured by a densiometer having a light source and a tiny aperture. Film is well suited for relative dosimetry of electron beams, where it shows practically no energy dependence. In photon beams, it shows significant energy dependence, and therefore it is used mostly for portal imaging, which I remember back, I suppose it was 2004, 2005, when you didn't have the onboard imaging, you would actually have to take a set of orthogonals. And I was always amazed at the ability for therapists to be able to set those things up, get them developed and whatnot. That was a real production. Nowadays, since you have a lot of onboard imaging, you don't really have to worry about that kind of thing so much, at least in that particular aspect of radiation therapy. So it's made a lot of improvements. And it can also be used for quality assurance procedures such as checking beam alignment, isocentric accuracy, and beam flatness. One thing that I do see film used for quite a bit, at least in our clinic, is used to measure what electron doses are on a patient. Like a doctor would come, would say, I want film to be placed on this particular patient, like at the surface or at a particular spot, in order to be able to measure what the actual dose is. And film, when properly prepared, can be really great for that. So for measuring dose distributions, photon energy dependence must be taken into account. Radiochromic film has a major advantage, which includes almost tissue equivalence, high spatial resolution, large dynamic range. In other words, 10, I think that's supposed to be, not exactly sure what that is, but I don't know if it's 10 to the -2 or if it's 10 to the 6th. But anyway, there's a wide range of energies for which you can use it. There's low energy dependence. Insensitivity to visible light, so, exposure to visible light is not necessarily a thing that will worry you, and there's no need for processing. It is well suited for dosimetry of brachytherapy sources where the doses and dose gradients close to the source are very high. That's one of the things about film that allows you to be able to it will pick things up. It will pick up gradients quite easily, and not every detector out there is really set up to do that. So if you want to know more about how these particular devices work, you can see here, you've got, let's see which section this is in. This is in certain solid state methods, and let's see, other methods of measuring absorbed dose. So that's what's being covered here. May have a few problems on those a little bit later. It might take me a while to kind of put those together. But I wanted to introduce to you what was going on in this particular section before you try to read it, because some of this, if I go through and just try to explain it to you, and you might sort of lose where these things are coming from. But I have found that if you go through and if you look at the summaries first, and then you go back and you start to look at the sections, then you have a much better chance at grasping what it is that they're trying to say. So as there are problems in this particular chapter, I will try to reference back to these particular formulas. Again, this book is covering the physics of it, of what it is that we do, but I'm also trying to tailor what it is that's going on to the audience of a radiation therapist, and you guys don't necessarily need all of that particular detail. Is it good to have? Sure. If you want to go on to physics, you got it. But I'm not interested in delving too deeply, because I want us to be able to get the general concept, and then we'll work on the details as we go along. So hopefully that was helpful, and I will be talking to you soon.